All right, in this video I wanted to do just a couple examples of applying Ampere's law to find the magnetic field due to certain current distributions. So we learned about Ampere's law where it's really similar to Gauss's law in that it's an easier way to find the magnetic field for particular types of current distributions. And so that's Gauss's law is an easier way to find electric field for certain charge distributions. The difference is for Ampere's law, we're looking at a line integral, which means we've chosen a path and we're going to integrate around the path. The path has to be closed. That's what this circle means on the integral sign. And what we find is that that integral would be equal to mu naught, which is just a constant, times the current that we enclosed in our path. We do have to choose our path in a certain way. We would like the magnetic field to be constant over the path and ideally parallel or perpendicular to the path, depending on the situation. We're going to see both of those being used. So here is our first example that we're going to use. You might think that this is just going to be like a long straight wire, and in some ways it is, but it is a little bit different in that the current is distributed over a finite cylindrical shape so that it's spread uniformly over that entire cross-sectional area. If you take the entire cross-sectional area, you would get the total current, which is I. We are going to look at two regions. We're going to look for R outside of the cylinder and for R inside the cylinder and see the expressions for the magnetic field for both. We're going to start with the easier part, which is outside of the cylinder, and this is this path of integration right here. So we're doing B dot dl. The idea being that we know the magnetic field will form a circle around that wire, and so we're choosing a circular path. That will make the magnetic field tangent or parallel to dl the whole way, and it'll also be constant. Because it's parallel, the dot product just changes to the product of the two quantities, and because the magnetic field is constant on that path, we can take it outside of the integral. And then this is just the circumference of the circle, which is just 2 pi r. So we've gotten on the left-hand side of this expression of Ampere's law, we got B times 2 pi r. How much current have we enclosed? We've enclosed all of it, so we'll say I, and we can solve for the expression of the magnetic field, and it just looks like a thin, long straight wire. So the idea is as long as we're outside the cylindrical conductor, it'll look just the same as the magnetic field due to a thin, long straight wire. Now let's look at what happens if we look at a distance that is within the conductor. Now for that, we're looking at this expression. We assume that the magnetic field inside will still look the same in that it'll form circles. That means that for our integration, the magnetic field and dl are parallel to each other. And we also expect the magnetic field to be constant on that path. And when we integrate the entire path, we're still going to get 2 pi r. Now the idea here is, though, now we have to worry about this. What is the current that I've enclosed? So we're going to use the fact that the current is evenly distributed over the entire area, over the entire cross-sectional area. So we're going to look at current over area. So if we want the entire current, we would have to look at the cross-sectional area. This is the cross-sectional area here, which would be equal to pi r squared, where we're using big R, because this is the actual radius of the cylinder. So if we look at that area, we will get all the current. What we're trying to figure out is how much current do I get when I'm looking at this little r, this r right here, squared. So we can just rearrange this, and basically what happens is we are going to be enclosing a fraction of the total, because this is going to be less than 1. So the amount of current we enclosed is some value that's less than the total current. It would only be equal to the total current as we got to the edge of the cylinder. So I did a little bit of rearranging. I didn't talk much while I was doing it, but what we're going to find is our magnetic field is going to be increasing as R increases. At the time when R would be equal to the radius of the cylinder itself, you can see that what we would get would be mu naught I big R, or 2 pi R squared, which would just be mu naught I over 2 pi big R. So it ends up looking like the value it would have outside the cylinder as we get to that surface of the cylinder. All right, now we're going to look at another very common type of magnetic field production that we are interested in, and it's when we create what we call a solenoid, which is a tightly wound coil of wire. The idea is to try to make a nice uniform magnetic field down the center. If we used our right-hand rule and we see at the front of the coil our current's pointing down, and we do our right-hand rule, we should convince ourselves that the magnetic field that is inside should be pointing to the right. And basically what's happening is, because of this, we're trying to make it relatively uniform within that coil so we can create a nice constant magnetic field. Let's use Ampere's law to derive the expression. Now, this is a little bit different. What we're doing is we're doing a cutaway version, a cutaway view of the solenoid, which basically means we're going to chop it in half. And so here we can see that we're looking at half of the coils, where here the current at the bottom, the current's coming out. At the top, the current's going in. Again, I can use my right-hand rule, and you should be able to agree with this direction of the magnetic field is going to be pointing to the left in this situation. Now here we're going to take an interesting path. We're going to do a square path for our Ampere's law. The reason for this is we're going to have different results in each part of the path. So I'm going to do, first I go from A to B, a B dot dl. Then I'm going to go from B to C, a B dot dl. Then I'm going to go from C to D, a B dot dl. And then I go back D to A of B dot dl. So what I've done is I've broken up the entire closed loop into 4 different parts because I'm doing a square. I want to look at some of these different pieces that it might be easy to figure out. Notice that when I go from C to D, I am outside the solenoid where I expect the magnetic field to be 0. That's this one. It's going to contribute 0, so we can get rid of that. The other 2 sides that are of interest are here and here. Here there's a combination of things coming. Either B is 0 near the top of these paths, but when it's in here, B is perpendicular to my integration, so B dot dl is 0. So on the 2 sides of my square, my integration is 0, either because part of it is outside the solenoid where the magnetic field is 0, or it's inside the solenoid, but my path is perpendicular to the direction of the magnetic field. So I'm going to get rid of D to A and B to C. So the entire path has been broken down into just one little piece of B dot dl when we go from A to B. The magnetic field's going to be constant there and parallel to the path. And so we get that. So right now I have B times dl is equal to mu naught. And now how much current have I enclosed? Well, each turn has a current of I, and if we use N is the number of turns that we have, that's the total amount of current that I'll enclose. When I integrate over dl, notice that's going to be the entire length. So I get B times L equals mu naught N I. And so if I rearrange this, I get B is equal to mu naught N over L times the current. So in this thing, this is held the total number of turns, and this is the length of the solenoid. Sometimes we write it as mu naught little n I, where little n has taken the place of the number of turns over length. N is number of turns per length. Oh, I should have written it here. So B can either be written as mu naught N over L times I, or mu naught N times I, where this is the number of turns per length. In this picture, it has a more accurate representation of what the magnetic field will look like. You do see that near the ends, it's not quite as high as it is in the middle, but we get sort of a nice length of uniform magnetic field for the most part in the very center of the solenoid, which is why we make these in the first place.